we still have derivatives about 1. If you take the derivative of this transformation, the derivative is close to 1, and it can be too small. Because if you have small derivatives,
it prevents the small derivatives. If the filter we have such a filter that it shows 0, we still add 1 because of the x.
yes. We still and in this way we propagate this derivative. So what basically we have many layers. Let's suppose that we have function j at layer j1 at layer 1. Function j3 at layer 3. And if suppose we have a single parameter at layer 1, and to compute the derivative of this function, it is dj3 by dg1, dg2, dg2 by dg1, and dg1 by dg. And these guys, first two terms here, are defined by this transformation f of x plus x. And if this transformation has small derivatives, or we have some error in the evaluation of the derivatives, then the product also would be small, and our moving into the right direction by the gradient descent would be not small enough. Basically, our different layers would be learning at different speeds. Top layers, when we take less number of these intermediate terms, would learn faster, but some core layer, that are very important for our method, would learn pretty slow, and it is a problem. You can try it. These modern architectures, you can use Google Cloud to optimize ResNet, smaller ResNet model, and see what would be the result if we get rid of skip connection. At some number of layers, you will see that everything will fail. Basically, in 2014, when the first variant of convolutional neural networks that developed for ImageNet scale datasets were introduced, the number of layers in AlexNet, I suppose, was something like maybe 8 to 10 layers with this order of magnitude. And it was because we can do better. At that moment, we didn't have this idea of skip connection, of remove the head. And because of absence of this idea, because of absence of the idea of optimization layers, we could not learn bigger models, deeper models. But introduction of the skip connection allows to learn models like the 50 layers. And you can see this benefit in practice. It's not so theory, it's more like an engineering trick to make everything. Yes?
I have a question. If you have a large model, the deep neural network, can we use different data parts for training different parts of our model, and can it be helpful to prevent overfitting maybe?
So you want to update on a part of the model?
No. For the one data, I can update, for example, the first part, and for the second data, the second part, and чередовать.
Yeah, skip these two things. I think that optimization is this way is not a correct problem. So basically, suppose you're saying, okay, you have two functions, yes, two loss functions. One loss function for one batch of the data.
No. It's a part of neural network, so we just...
You freeze some part of the...
Yeah, just evaluate.
This is called a dropout. You can read it at home. How it can be implemented. Dropout. Basically, at each training step, we drop like 50% of all the weights randomly, at random, and train only the remaining ones. And because of this, we do reduce overfitting. That's it. Also, very important trick. I agree, and we are better guys that invented it. And if you know it before or not. But yes, it is a crucial thing to reduce logic. Basically, we can say that it's equivalent to some type of Bayesian generalization, if you like Bayesian things. But basically, okay, it's just reducing the number of parameters. Yeah, anyway. Okay, and last thing I want to talk about is polymaths. Very simple. I will show you a figure, and I hope you understand everything. Okay, we have a matrix 4 by 4. We need to have a matrix 2 by 2. What we can do? So we want to reduce each dimensionality to 2 times. That would be a matrix here, 2 by 2, and take the maximum value in this submatrix. Then, another matrix 2 by 2, let's take another maximum, and so on. We divide all our matrices to blocks 2 by 2, our X or R subvalues, and produce this type of transformation. And basically, typically, we take the maximum value here, and so this way we reduce the dimensionality of our matrix, and we have small dimensionality of an output of a single layer. One can also argue here that this operation is not very well differentiable, the maximum. But again, it's enough to do what we do. It just takes a derivative, because we can assume that the maximum does not change, and we have specific element equal to the maximum of each part, and take its formulated derivative, and it's enough to make it. And basically, this pooling layers allows the reduction of dimensionality, and at some point we combine all these type of layers to get the final layer before generating answers. Typically, some break small matrix is the sum with number of channels. For example, matrix 5 by 5 and 25 channels. And by multiplying all this, we would have dimensionality 625, and then we apply the pair or 2 arithmetic pairs to get our properties. And that's enough. So basically, we combine the layers like convolutions with filters and skip connections with these pooling layers, and inside these filter layers we also have nonlinearities, and it's enough to make everything work. Okay, I skipped a few details, but I suppose they are not that important for now. You can look at specific ResNet architecture and split into specific layers and look at each layer, and I suppose it will be useful exercise, especially given that you are going to repeat this exercise at the different levels. Any other questions on evolutionary methods?
Can we compare
So the maximum?
Yes.
To some extent, yes. Formally, we can say, okay, we have as a maximum element, and so we have this maximum output t, and we can define the derivative dt by dt, and that's okay. Yes, the maximum can change, but don't care about it. Yes?
Do we have some data-dependent pooling method that will prioritize different pooling positions based on the data you have?
Okay, I suppose if you want, you can find tens of papers on this, but actually in real ResNet, no one is doing this.
Okay.
Yes?
It was stated during the previous seminar that the typical convolutional layer has not a single kernel or filter, but several filters for several channels. So why do we apply different kernels for different channels?
Because it works better. Okay, nothing specific reason. No specific reason, just you can try this way, okay, this way better, so let's do this. Little theory, independent product.
So, but the number of parameters in